Team Arrow, representing Nirma University, India, presents its Flight Readiness Review for AUVSI SUS 2022. The OS is Team Arrow's 2022 UAV. This year, the team has decided to go with a multi-rotor design, specifically an octocopter configuration, which has been designed and fabricated ensuing extensive research and development. Integrating rigorously tested subsystems, the team was able to develop a UAS capable of surpassing the challenges laid out by the AUVSI SUS while still being in compliance with the competition regulations. Mechanical system overview. Various composite materials were considered and ultimately carbon fiber was chosen due to its lightweight and high strength to weight ratio. The landing gear upon which the UAV rests was built using carbon fiber, MJF nylon and silicone. A completely different and unique design was chosen for the landing gear mount. This was possible by implementation of generative design which maximized stiffness for the least mass possible. To ensure smooth landing, silicone shock absorbers were used. Our unmanned ground vehicle for the task of payload delivery is supposed to be airdropped through a winch mechanism. The UGV is made using the same carbon fiber as used in the UAV. Our design and construction ensure good grip and are effective on both sand and gravel terrain. An antenna tracker was developed using stepper motors and 3D printed parts. Electronics System Overview. For autonomous flight, PixarCube Orange with Year 3 GPS is used. Similar configuration is used for the UGV as well. For the imaging system, Canon EOS M200 is interfaced with the Jetson Nano, which deals with capturing images, geotagging, and file encryption. For communication, Ubiquiti Rocket 5 AC air module and Ubiquiti Lightbeam 5 AC ground module are used. Software System Overview. The team chose Mission Planner as its ground control station as it offered great support for customization, was reliable, and team had prior experience with the same. The team also uses OpenDrone Mapping, an open source photogrammetry tool, to stitch all the images captured by the imaging system and form a map based on the geotags. This year, the team is planning to attempt the following: autonomous flight with high confidence, object detection and classification high confidence, object localization medium confidence, static obstacle avoidance high confidence, not attempting dynamic obstacle avoidance, mapping high confidence, airdrop high confidence, and UGV drive to location medium confidence. The arms of the UAV are made of hollow carbon fiber rods held between 3D printed PETG clamps. Thus, they needed to be tested under highest possible loads and checked for deformation and maximum stress. The maximum deformation obtained was 3.408 mm and a factor of safety of 3. This ensured the design's airworthiness. The team also ran propeller thrust bench tests to validate the UAV's expected thrust to weight characteristics. A CFD analysis was also run on the octocopter's propeller to further validate the aerodynamic characteristics of the octocopter. The main camera is coupled with the Jetson companion computer. The imaging system handles image capture, geotagging, and file encryption. The photos are then resized and are transferred to the GCS via the Ubiquiti Wi-Fi link. After meticulous testing of the autopilot, the team successfully performed auto-training of the UAV to get the PIDs well tuned and for the vehicle to achieve impeccable takeoffs, cruising, and landings to ensure upright flights in extreme weather conditions. The team has developed a GUI-based Python program that would support image cropping and detection of its characteristics. The team will also be geotagging the image. The geotagging of each image has also been triangulated with an accuracy of up to 7 meters. An error of around 15% on an average was detected when compared to the actual GPS location, which was obtained through a phone. The test was conducted on around 48 images for the autonomous ODLC task, and the team has found that the total accuracy of the algorithm is 70%. The alphanumeric has an accuracy of 76%. The color has an accuracy of 83%. The shape has an accuracy of 92%. Due to insufficient accuracy and negative scoring, the team shall not be attempting the auto ODLC this year. The team developed an ODM-based implementation. On an average, a usable map is obtained in 7.2 plus or minus 1 minutes. An inpainting technique was also developed in case of information loss and stitching errors, which works as a pre-processing step for the Mercator wrapper. The open source ODM proves to be an industry standard, sufficient for the tournament's high standards. The companion computer retrieves the GPS data concurrently while triggering the camera. The picture is data stamped and sent through the Wi-Fi, producing a map of superior quality. The team offered the novel empirical analysis of 5 different motion and planning algorithms and decided on a hybrid imitation learning approach. A CNN LSTM network was trained and experimented with various expert algorithms for behavior cloning paradigm. A simulatory platform was then created mimicking the tournament's obstacles, based around the objects following variable radii and superimposition. But in the end, the classical path planning algorithm A* was used to compute the path. Due to unmatched drop accuracy and safe delivery of the UGV, winch mechanism was chosen over the parachute. A DC motor is used with an Arduino Nano interfaced with the Pixar. This enables the winch mechanism to lower the UGV in a controlled descent. 2 linear actuators are then used each on the UAV and the UGV to minimize oscillation and ensure timely release of the payload. All systems were individually ground tested. Following that, full system bench tests were performed on integrated systems. After integrating all the subsystems, full system flights emulating compression tasks were flown and performance was evaluated. Each revealed flaws and necessitated process refinement in order to broaden the team's overall reach. The team found out that it needed to work on the UAV's stability and mainly on increasing the endurance. The focus was then diverted to reducing the overall weight of the UAV. The team also attempted to complete all the tasks within the stipulated time but fell short on the post-processing time. Thus, optimization of the post-processing methodologies was required. Pertaining to the Wi-Fi link, there was a loss of data packages, as a solution to which the team developed an antenna tracking system. The team was especially concerned about the UAV's stability while performing the airdrop. The winch mechanism was fine-tuned to drop the UGV in a controlled manner in accordance with the UAV's state. Firstly, the UAV was auto-tuned and winch mechanism was tested with a dummy payload, ensuring sufficient thrust-to-weight ratio required for the drop. Then the UAV itself was also tested to be airworthy in case of any instability caused due to the drop. Geotagging of the image had an error due to latency in data transfer between camera shutter operation and GPS data retrieval. Thus, the team worked on an algorithm which compensated for this by calculating the latency and geotagged the image accordingly. Various safety checks and protocols were developed and implemented. This ensured that there are no unforeseen accidents at the flight line. The team has also prepared for various fail-safes such as geofence breach, communication loss, GCS malfunction, etc. To overcome these, the team has designed a UAS with high degree of redundancy on the UAV as well as the GCS. These practices have instilled a sense of professionalism and situational awareness within the team pertaining to the competition.